This is our fourth day of interaction. First day we started with the mechanical properties and we defined the texture, how it affect or what are the factors involved in terms of measuring texture. And then we talked about mechanical properties. Then we went to viscosity measurement. During the viscosity measurement session, we didn't do a lot of calculations. I just ran through that. So we will do those calculations now, part of this section today. And then we talked about viscoelastic properties. And yesterday, primarily we focused on TPA of dairy products or solid materials. Then after TPA, we discussed about functional properties, melting, stretching, melt profile, modified Schreiber test. Those methods we discussed about that, and then we looked at the different measurement we can do with the dairy products, and finally we talked about the sensory analysis of texture. How do you do the texture using the sensory analysis? This morning we are going to do viscosity, measurement of viscosity using sensory methods. Then we are going to talk about the typology. After the lunch break, we come back and finish up the advanced methods or advances in methods of measuring texture and rheology. Okay, let's start. Any questions anybody has before we start the discussion on viscosity using the sensory methods? What is the viscosity in terms of the sensory analysis? How do we, or anybody here, if you want to measure the viscosity or define a viscosity as a human or as a consumer, how do we do that? Any thought? Let's say if I give you 3 different fluids and then I ask you to differentiate between 3 different fluids, how do we do that?
Based on the density.
Yeah, you can, based upon the density, you can probably pour and see whether it's pouring faster or pouring slower. So thicker fluid will flow slower, thinner fluid will flow faster. Time it takes to flow would be less for the thinner fluid, and it will take more time to flow for the thicker fluid. So that's one way to do that.
When we touch finger, we can feel viscous.
So you can also use your hand, and you can probably just take a small amount of fluid and then rub it and see whether it is kind of thick or it's a very liquid kind of thing. So from that you can also do the differentiate between the samples.
And also in your mouth, when we feel by our tongue also.
Exactly. You can also put it in your mouth and then have a palate going and then see how thick you are feeling and how thin it is, like that. So again, we are talking about the density of the material. So that is probably one way to do that. Any other way we can do the viscosity? How about if you have a fluid in a container and then you have a spoon or something? So if you stir it, then you will know that if it is a thicker fluid, you will have more resistance. It will be harder for you to shear compared to thinner fluid, less viscosity. So these are all with the assumption of fluids are behaving like a Newtonian fluid, right? That's only thing we can do. They cannot, as a sensory person, through sensory analysis, we cannot do more than that, right? Because the other things are based upon different behavior. If they are not Newtonian, they are non-Newtonian behavior. So and then sometimes they will have a yield stress also. So that will so we cannot really characterize the fluid. All we can do is measure the viscosity. I mean, at least give a meaningful information. One is higher viscosity, other one is less viscosity. Or if you have 4 or 5 different samples you want to differentiate, you can probably put them in order. With different people may put it different order, but at least the highest viscosity will be in the one extreme and the lowest viscosity will be in the other extreme. In between, there could be different way of arrangement. Make sense? Pooja may do that. Okay, if I give 1, 2, 3, 4, 5, she will definitely put 1 as a 1, 5 as a 5, and then between 2, 3, 4, it could be 2, 4, 3 or 3, 4, 2, 3, 2, 4, something like that, right? I mean, because it all depends upon what would be the range in terms of the viscosity, difference in viscosity. What I'm trying to say is, let's say if there are 5 different viscosity samples, if 5 is the highest viscosity and 1 is the lowest viscosity, then this 2, 3, 4 can be like that, or it can be 3, 2, 4, or it could be 4, 2, 3. In any order it can sit, right? Because if the 5 is the highest viscosity, let's say the viscosity value is 10,000 Pascal times second, which is very high viscosity, right? Because water is 1 Pascal times second. So it's 10,000 Pascal per times. The lowest is 50 Pascal times second. So if the other 3s are falling in between, then everybody can come very close to that arrangement. They can differentiate in a specific order. Everybody will do that. On the other hand, this is lowest is 50 Pascal times second. Highest is if it is only 50, 200 Pascal times second, the 50 and 200 is very nearby. So if these 3 samples sit in between, then there is a very good chance that everybody may not have the same order compared to instrument method. But at least this gives some idea about how people will differentiate. Because it's not like a taste, or it's not like other evaluations. It's primarily it's a mechanical evaluation, right? And the viscosity is just one property. We are not talking about anything else here. So in that case, this is the best probably we can do. So what is the viscosity in terms of sensory analysis? I think we already talked about it. You can probably put it in the spoon and then you can slurp it. So and then you can see how easy for you to slurp it or how difficult it is for you to slurp it. Higher the difficulty, higher viscosity. Easier slurping, lower viscosity. That's how much we can. So degree of viscosity is measured as the force required to draw the liquid over the tank. So I think this is probably best way to this is best way to evaluate the viscosity in terms of the sensory analysis. So why should we measure viscosity? What's the big deal about that? Any thoughts? Not even looking at this slide. Why we need to care about viscosity? In terms of product development, I'm not hearing you. Flow behavior? Yeah, I mean, basically we need to know the viscosity measurement. We can obtain the much useful behavioral and predictive information of various products, wherever we are going to apply or what kind of products we are going to develop. So we need to make sure that we have right amount of viscous nature, flowability behavior. So that's important. In terms of quality control, viscosity play a big role also. Like texture, viscosity play a big role. Um, and because of the viscosity only will dictate the raw material selection, because whatever you put in to make your product, that will dictate how the viscosity is behave, or what kind of measurement you are going to make. So, and that is very important for the food industry. Oh yeah, exactly, yeah. So how much you want to have hold it, or what kind of strength of packaging material you want to have, so that will have impact also. So that's a very good point. And also you want to make sure that you have the consistent raw material, so that you every time you develop some products will have a similar viscosity, and that's very important. Uh, so here also for this purpose, flow behavior is an indirect measure of the product consistency and quality. So how well the product flows, that will dictate also. Um, so how is the sensory evaluation used for viscosity? If you look at the food companies, sensory scientists work closely with the product developers to understand which viscous properties of food material would be perfect for the industry. So they like to know what consumers like and why they like that way. So if consumers tell a difference when they change a product, so or substitute an ingredient, so that will allow them to work on better product, and that will the bottom line for their economics of the whole industry. At the end of the day, they have to make money, right? So they need to make sure that they satisfy consumer needs, and so that they give the quality product for the consumers. In academia, sensory scientists or engineers, we try to understand how our sense work and respond to viscous foods. Uh, that's what we try to do in terms of the sensory scientist. That is their goal for them to do this kind of sensory work. Some of the factors affecting viscosity, whether the flow is laminar or turbulent, influence the viscosity. If you are pushing the fluid faster in turbulent manner, the viscosity may be get reduced. And if you move the fluid slowly, the viscosity may be higher. And so flow conditions will make a difference also in terms of the viscosity. The other properties, temperature is very important parameter, right? Higher the temperature, uh, they will make the fluid flow faster. So that's also important factor. So when temperature increases, particles of the liquid are excited and can flow more easily. And the viscosity of non-Newtonian fluid changes with the shear rate, correct? So non-Newtonian fluid either shear thinning or shear thickening. So they will have influence on how fast you shear them or how slow you are shearing them. That will have influence on the viscosity measurement. Even sensory people we are talking about, not about the instrument measurement, but the sensory people will themselves will be able to give differentiation in terms of the how they feel about the viscosity. Viscosity and texture. If you just look at the viscosity and texture, as the name implies, the distinction between the texture and viscosity seems very simple, because texture applies to the solid foods and viscosity applies to the fluid foods. But people often use the expression thin or water-like liquids that have low viscosity and thick as a traggle for liquid with high viscosity. So viscosity is an important parameter, as it can be used as an indicator of the quality by the consumer, for the consumer. So and also we know that viscosity of different fluids has an influence on shear rate, how much we are shearing. So higher rate of shear making the fluid thinner compared to the fluid that was sheared more slowly. So that's why we call it a time independent steady state flow or pseudoplastic behavior. So if it is a Newtonian behavior, viscosity will be constant, one number, right? But if it is a pseudoplastic, that is the shear thinning. Viscosity will be decreasing as you increase the shear rate. And for the shear thickening fluid dilatant, the viscosity will be increasing with respect to shear rate. This is first time you are seeing this graph, because so far we have been looking at the shear stress and shear rate. This is basically taking the slope of that shear stress and shear rate and giving the viscosity values as a function of shear rate. Pinkham plastic initially will have higher yield stress, then the viscosity will be decreasing. And it's a pseudoplastic with yield stress, again similar to Pinkham plastic material. Now let's look at some of the viscosity measuring instruments. This one is a consistometer. Primarily it's a Bostwick consistometer or Bostwick viscometer. Very simple instrument in the food industry, which determines the consistency of the food by measuring the distance it flows under its own weight. So basically you keep your product to be tested here, and then there's a gate here, and then as soon as you lift the gate you time it, or there is a scale here, then you can see how far it goes, and that could be one way of indicating the viscosity of that fluid. So if the sample is sticking to the instrument, they are really highly viscous and do not flow sufficiently in 30 seconds. So higher the viscosity. But if samples are flowing faster, then it is the low viscosity fluid. What you see here is the falling ball viscometer. This type of viscometer has been used in several industries, including the food industry. This is primarily based upon the density of the material. Whatever liquid you want to measure the viscosity, you need to know the density of that liquid or fluid, and also there is a falling ball you inserted here, and that has its own density. So because of the density difference, you can calculate the viscosity of the fluid here. So that's a principle here. So it's a function of viscosity is equal to ball constant times the density of ball minus the density of liquid times the time it takes to travel from point A to point B. So and here this is called dynamic viscosity, because it's nothing to do with whether fluid is Newtonian or non-Newtonian. Only if the fluid is Newtonian or non-Newtonian characterization, then you can call it apparent viscosity. So this is why it's called dynamic viscosity, because you use the density difference when you are trying to calculate or measure the viscosity of the fluid. So it's a function of density of ball minus density of liquid times the constant and also the times the how much time it takes to travel the distance. So let's try to okay. In this instrument, it's like a Brookfield viscometer. You all remember Brookfield viscometer I showed you yesterday, not yesterday, day before yesterday, where they have different spindles, right? So depending upon this, what fluid you are going to test, you have to select the right spindle. Same thing here also, depending upon what fluid you are testing, there are 6 different balls they have it with the instrument. So you have to select the right ball so that you can measure the correct viscosity. That's the limitation of this instrument. It's not just one ball, you can use it for any fluid you have. Ball constant is primarily based upon the dimensions of the ball and the density of the ball. It comes with that. They do standardization procedure and they get the ball constant value. It is like any equation you take, there's always the constant numbers for that equation, similarly like this. But this ball constant is different for different balls. So it's not the same ball constant for all the balls. Okay, let's assume that we have a falling ball viscometer, a standard ball. Here ball constant is 0.1 millipascal times second, was used to measure the dynamic viscosity of a fruit juice. The ball took 20 seconds to pass from point A to point B. Calculate the dynamic viscosity of fruit juice sample if this juice density is 1.1 gram per centimeter cube. So equation is viscosity is equal to ball constant, K times density of ball minus density of liquid times the time it takes to travel the distance. K is 0.1 millipascal times second. Density of juice is given 1.1 gram per centimeter cube. Density of ball is not given here, but I know for sure it's 5.8. So time is 20 seconds. Four point eight. Pardon me? Oh, 4.7. I'm happy that you guys are not sleeping.
The density of ball, it is given absolute.
Yeah, it's not given in the problem statement. It's a constant value. I found it in the literature. So that's why I got the 5.8 there. So it's 4.7 times 0.1 is 0.47 times 20 is equal to 9.4 millipascal second square gram per centimeter cube. That's a very good question. I'm not sure. Maybe the equation may not. Well, I know for sure equation is correct, but I'm not sure that the ball constant has a unit. I will check on it and come back in the afternoon. Okay, because it cannot be constant, right? I mean, ball constant means it should be a number only, not the unit, right? So I'm not sure why it's they have millipascal times second as a unit. That's a viscosity unit, correct? So I need to check on it. I will check on it and then I'll come back in the afternoon with the correct information. Okay. Yeah, I don't think that is right. I think this millipascal time should not be there. So it is. So other instrument is capillary viscometer, known as U-tube or Oswald, measure the time of fluid to pass between the 2 points in this capillary tube under the force of gravity. This is only suited for low viscosity fluids, Newtonian fluids, low viscosity Newtonian fluids. Higher viscosities, then we need to go with the rotational viscometer, and that's the best option we have it for us. The next one is capillary tube viscometer. The principle involved here is you basically flow the fluid from point A to point B point A to point B. So there will be pressure drop because of that. So delta P is a function of the viscosity of the liquid. So based upon pressure difference and the radius of the tube and the length of the tube, you can calculate the viscosity. The equation for that is the shown here. Viscosity is pi times delta P times radius to the power 4 divided by 8 L V, which is volumetric flow rate. So delta P unit is Pascal, radius is meter, so meter to the power 4, and the length is meter, and volumetric flow rate is meter cube per second. So meter cube, meter power 4, so unit is Pascal times second. Makes sense, right? That's a viscosity unit. That's what we got. So let's try to solve this problem. A capillative viscometer is being used to measure the viscosity of honey. So what kind of fluid is honey? Newtonian? Newtonian or non-Newtonian? Newtonian. Everybody agree with that? We will find out. We will do the calculations for this data and see whether we get the Newtonian behavior. If we do 2 or 3 of them, so they should have the same number, same viscosity value, then it's a Newtonian fluid. The tube radius is 2.5 centimeter and the length is 25 centimeter. The following data have been collected. Determine the viscosity of honey from the data collected. So let's use the equation. Mu is equal to pi delta P R to the power 4 8 L volumetric flow rate. So first data, pi times delta P is 10 Pascal plus U, radius to the power 4, radius is 2.5 centimeter, convert to meters to the power 4 divided by L, 8 times length is 25 centimeter, in meters 0.25, volumetric flow rate is 1.25 centimeter cube per second. We want to do it in meter cube per second. So 1.25 times 10 power
6
minus 6, correct. Please use your calculator or your cell phone. .14 times 10 times 0.025, 4 times divided by 8 divided by 0.25. Wrong answer. How much? 4.91. So let's do the last data. This day, this going to be different. Bless you. What's the answer?
4.8.
Let's do the middle number, middle data. Answer, please. This is first time I'm getting the same answers from everybody who is speaking up. In the last 25 years, I have been teaching this class to my students. This is first time I am getting the same numbers. So you guys know what you're doing. And you are all doing it correctly in the first, in the first attempt itself, it's great to see that happening. I know because you are all cream of the crop compared to what we try to get from our class, from our enrollment. So that's a difference. So questions. So based upon the answers, what do you think the fluid is? Huh? Huh? Where do you get the non-Newtonian? Okay, only viscosity changes has a trend, then you need to worry about non-Newtonian. The 4.81, 4.91, 5.11, they are all very close number. If it is, let's say, 4.91 and the next number is 4.1 and then next number is 3.4 like that, then it's a shear thinning. Right? You start with the higher viscosity and then it's going down, then it is the shear thinning, non-Newtonian. In this case, it's not non-Newtonian because the variations between the numbers is very, very small, and it's just a matter of, these are all very acceptable variations. So we really don't need to worry about whether this can be there is no differences at all, in my opinion. It's, if you look at the differences, it's only 0.2. 0.2 is something like a 5%, right? 4.91, 5% of 4.91 is how much? 4.91. 5% of 4.91 is close to 0.2, right? 0.25. Did I say it correctly? Yeah, exactly. So if you have 10% error, that's very normal because these are all actual experimental data. So that's why I'm saying that is very close number. So it's a Newtonian fluid. So, and that's what your hypothesis was, honey is a Newtonian fluid. That's what you got from measurements, and that's what we verified here with these calculations. Agree with me? Next one is rotational viscometer. I thought we have it in the lab, apparently not. So basically what it is there is a cup and there's a bob. Cup is in the outer is the cup and then bob is the inside. So material to be tested is put in between the bob and cup. So and then when you rotate the bob, what happens is there is a shearing going on between the bob and the sample, and based upon the viscosity value, the torque meter will experience more resistance or less resistance. Higher the resistance, higher the viscosity. Lower the resistance, lower viscosity. Yes, Nivedita. This is, yeah, I mean, yeah, exactly. But the issue with the Brookfield viscometer is you have to select the right spindle for your sample. And also, excuse me, Brookfield viscometer can give only one viscosity number. It cannot characterize your fluid. So that's why we have to use the rheometer for that. I mean, you have the rheometer, but we don't know the right attachment. Exactly. So, um, so basically, when you rotate the bob, the resistance offered by the sample will be recorded as a torque, and based upon the radius and height of the cylinder and all, you can calculate the viscosity, and the viscosity is function of torque. So viscosity is equal to torque divided by 8 pi square n L. N means rotation you make 1 over second. Length is cylinder height, and then radius, inside radius of the cylinder, Ri square. So if you substitute the units, torque is Newton times meter, 1 over second is the rotation you make, revolutions per second, and the L is the height of the cylinder, and radius is meter square. So the meter cancels, so Newton per meter square gives you the Pascal, and then 1 over second is second, Pascal times second. So that's the viscosity unit. Any questions on the equation? So let's assume you have a single cylinder rotational viscometer with 1 centimeter radius and 6 centimeter length is being used to measure liquid viscosity. The following torque readings were obtained at several values of the revolutions per minute. Compute the viscosity for different data here. Revolutions per minute for the first data 3, corresponding torque is 1.2 times 10 power minus 3 Newton centimeter. So let's go back to the equation, original equation. Mu is equal to torque divided by 8 pi square n L Ri square. So 1.2 times 10 power minus 3 Newton centimeter divided by 8 pi square times n is 3 revolutions per minute, but it is revolutions per second, 3 by 60 times the length is 6 centimeter, so you have to divide that by 100, you get meters. 1 centimeter radius, which is 1 by 100 meter square. Do we need to we need to do conversion anything? Yes. Which one we need to convert? Top one. We need to divide. We need to do what? You have to divide by 100. Answer, please. Let's do the last data point. Answer. We have to do one more, right? Because if this another number comes in between, then we may debate that it's a shear thickening, right? For all practical purposes. Uh, let's do that, right? I mean, what's a big deal now? It's from now. Answer? 0.4. So what kind of fluid is this? Newtonian only, right? I mean, it cannot be anything else. Whatever we have studied so far. So if the number is little bit higher than this and higher than this, then we would have said that it's a shear thickening. But it's very small numbers, and for all practical purposes, it's a Newtonian fluid. Any questions? Okay, what other way we can, in terms of sensory wise, measuring the viscosity? Well, not only viscosity, any other method for that matter. If you want to measure the stretchability of your product, cheese for that matter, what other way we can measure the stretchability of cheese, sensory wise? How do you do that? No, the issue here is, if you are going to measure the stretchability, not tensibility, stretchability, then your sample should be warm. It cannot be solid sample. Correct? I mean, no matter how much you try to stretch it, it won't stretch. Until otherwise there is some softening or melting going on with the cheese, then we can do that. We cannot do this. We can do other ways. What is other way we can do that? You can take a fork, and then your cheese is melted in a container or beaker or something, or petri dish or anything, and then you put the fork in, and then you can slowly raise it. But the issue here is, you want, as a sensory person, you want to make sure that you lift the cheese from the fork in a constant speed. Otherwise, you cannot really adjust things, saying that, okay, I want to get a good stretch, so I slowly do that, and then like that. You cannot do that. I mean, you need to try to maintain the same speed, so then you are mimicking the actual stretching test. I showed you yesterday also in the functional properties section, where you saw that they use the instron or texture analyzer. So they put the kind of fork only, put it there, and then the machine did the lifting. But here the human will do the lifting. So that's one way to measure the stretchability of cheese. How do you measure the meltability of cheese? Sensory wise. Huh? Yeah, you can take a melted cheese and put it on your tank and then see whether. Huh? Yeah, then melted cheese only you can say, or can see the whether you can measure the or evaluate the meltability, right? Otherwise, you can take the petri dish, put the cheese in there, melt them, 4 cheeses, melt it in the oven, take it out, and visually you see which one has a more spread. Then you can classify, you can rank them like that, right? By looking at it, visual appearance. You may not be able to get the actual number, but it's not about the number, it's about ranking. So you can rank them like that, right? Doable, I mean. So at least you can rank them, or you can put them in different highest melt to lowest melt. Any other ways we can measure the, we can sensory wise we can differentiate the samples? How do you measure the or, I don't know what we can measure. Ice cream. How do you evaluate the ice cream? Filling in mouth. Okay. So at least you can see how grainy it is, how smooth it is. So those kind of measurement you can do. Uh, what else we can do? Oh, okay. The pressing the ice cream with a spoon, and that will give indication of how firm it is, or how soft it is. That can be done. Any other?
Melting down dry test is there.
Yes, sir.
Melting down dry test is there.
Melting down right.
Ice cream is there, sir. We'll keep one measuring cylinder, a beaker. Above that, we'll place the mesh, and then we will invert the cup of the ice cream, and we'll calculate the melting rate of ice cream.
Oh, okay. But there also you are going to measure something, right? Not sensory wise, right? So I'm thinking in terms of sensory wise, what are methods we can, what other evaluations we can do for different products. The snack products we can do crunchy, right? You can bite it and then how crunchy it is. You can do that. And the solid cheeses, you can bite it. You can evaluate the how flavor of that cheese and things like that. That can be done, right? I think that's what they do in the when they do evaluation of cheese, sensory evaluation of cheese. How do they do it for paneer? They cook the paneer and then they evaluate it, or even they raw also. So what do they look for? Look for the because I'm not familiar with that. They look for the firmness.
Sponginess, it is not brittle, they check.
Break point.
Break.
Oh, okay.
And it is sour or not.
Oh, okay. Taste wise. Oh, whether it is acidic or not. Okay. Any other thoughts anybody has? It's easy. It's going to be easy. It's going to be interesting recording. So. So in this lecture, in this discussion, we talked about different ways of evaluating sensory wise, primarily on viscosity, but we also talked about other products, other sensing, other property evaluations, and then we looked at the viscosity calculations using different instrument, capillary tube, rotational viscometer, and I still need to check on the ball method, falling ball viscometer. I need to check on the units and make sure that what is the right unit. So I will come back to you in the afternoon when we meet after lunch. So next we are going to have a break for the coffee, tea, chai. Okay. And then when we come back, we are going to talk about the tripology. Tripology. Okay. Did anybody know what is a tripology is all about? No? You didn't have a curiousness, you didn't even check the Google search. One by one. Puja. Okay.
Something related to the surface, how the surface looks or how the surface will interact with surface interaction like that.
It's all about friction. All about friction. So that's what we are going to talk about. Friction, wear and lubrication. That is what the tripology is all about. It is gaining interest in the food industry, but this has been studied for many years in other industries, mechanical engineering, material science, physics, chemistry. They have been working on this typology thing many years. In fact, I found out that there is a professor here in NIT Roorkela. I'm not sure, I think he's in the material science department. He is the expert in typology. He should have been here in place of me, but I'm the official instructor, so I don't think we can get any. We cannot get any other invited speakers here for the workshop. So I have some example problem applications. I will explain the theory behind it, instruments available, and whole thing when we come back.